In this related rates problem, we have a skateboarder riding under a lamppost at a constant rate, and we're trying to think about how the skateboarder's shadow is changing. Okay, so let's draw a picture. So we have this lamppost that is 15 feet tall, and we have the skateboarder who's underneath it, so not drawn to scale, but who is 6 feet tall. And what happens with the shadow? Well, the lamppost comes down, hits the top of the light hits the top of the head of the skateboarder and continues all the way down. And this is the shadow of this skateboarder, okay? Starting here and going to the end. Okay, let X denote the horizontal distance from the base of the lamppost to the skateboarder, and S represent the length of his shadow. Okay, so I think we have our diagram here, and the skateboarder, it should be noted, is heading this way. So the skateboarder is heading away from the lamppost. Okay, so observe that the skateboard and the lamppost represent parallel line segments, and so we have that this and this are similar triangles. Okay, so there's a smaller triangle inside the big one. So let's use that fact to relate S and X. And one thing I want to note is that this whole side here of this bigger triangle, that length is X plus S, right? X is just this part, S is just this part, so the whole length is X plus S. Okay, so we can relate, let's say 6 divided by S will be the same as 15 divided by X plus S. And if we move everything over, try to get rid of those fractions, because we don't like taking, well, we can take derivatives of fractions, but it makes things a little bit more complicated. We get this, and in fact, if we multiply through by 6 on the left side and pull that over, we'll get 6x is equal to 9s. Okay, so an equation then that will relate dx dt and ds dt. If we take the derivative on the left side, we just get 6 and then dx dt because x is changing with respect to t. On the right side, the derivative of 9s is 9, but then ds dt because s is also changing with respect to time. So at what rate is the length of the skateboarder's shadow increasing? To me, that is asking, what is ds dt? At the instant, the skateboarder is 8 feet from the lamppost. So when x equals 8 feet. Okay, so we're missing a little bit of information. Up here at the top, we haven't used the fact that the skateboarder is moving at a rate of 3 feet per second. So from top, from above, we know that dx dt, right? Because if you think about it, the lamppost is fixed. So if the skateboarder is moving this way, dx dt is going to be the speed. S, on the other hand, is a changing variable. Your shadow is growing as you're moving away from the lamppost. So you don't want to measure the speed by doing ds dt. We're wanting to measure the speed by comparing the skateboarder to something that is fixed in place and not moving. So dx dt is going to be 3 feet per second. And that's also from the beginning how I knew the skateboarder was moving away from the lamppost, because it's a positive 3 feet per second. Okay, so I'll plug it in and I'll get that 6 times 3, so this is from here, 6 times dx dt, so 6 times 3, is equal to 9 times ds dt. So you see what's interesting is we actually didn't even use this, that x is 8 feet in this problem. We actually don't need x or s to be able to figure out how the rates are related. And that's sort of special to this problem. Sometimes you need it, sometimes you don't. In this problem, we didn't need it. So ds dt ends up being 6 times 3, which is 18 over 9, so 2 feet per second. Okay, and again, it's feet per second because the length of the shadow is measured in feet. Okay, and then it's changing with respect to time. So part E, as the skateboarder's distance from the lamppost increases, is his shadow's length increasing at an increasing rate, increasing at a decreasing rate, or increasing at a constant rate? So what I would say is that we can compare that ds dt is equal to 2/3 dx dt. Again, this is coming from this formula. And so what this means is that since dx dt is constant, right, the skateboard is moving at 3 feet per second, that the shadow length is increasing at basically a constant rate. And that's actually why we didn't need x or s to compute the rate. Okay, so what's moving more rapidly, the skateboarder or the tip of his shadow? Well, so the skateboarder was moving at 3 feet per second. The shadow is growing at 2 feet per second, but we're talking about the tip of the shadow, not the growth of the shadow. So the tip of the shadow is going to be this length here, right? So again, the lamppost is staying still. So if you're measuring how fast this point is moving, compare it to something staying still. So find how fast this is changing. So I would say the tip of the shadow. And my justification is that, oops, not that, its velocity is the sum, or I would say it's s plus x, that distance, that derivative, which is ds dt plus dx dt. So if the skateboard is moving at 3 feet per second, oops, this would be the shadow first. If the shadow is increasing at 2 feet per second and the skateboarder is moving at 3 feet per second, then overall the tip of the shadow is going to be moving at 5 feet per second. Okay, so think about the distance from the lamppost to be able to answer that question.